Anybody have any problems from the homework that you'd like me to go over, the units and scientific notation stuff? That is due tonight by midnight. Yes?
Go over the sheet, how we get it.
Yeah, sure. Okay, so this is one where you're going back and forth between prefixes, basically. So in every case, we're starting with 15.5 kilometers, which is kilo and then meters. And in the first one, in part A, we're going from that prefix of kilo to no prefix at all, just straight meters. In all the other ones, you have to go from the prefix to no prefix and then back to a new prefix. So let's just do a couple of those so you can get used to the sort of flow of it. Remember that going from, so if you have a prefix and you're going to no prefix, that's the super easy one. That's the one where all you do is replace the prefix with its mathematical meaning. But then the next step on all of those would be to go from no prefix to a prefix. And that one is kind of like two steps, I guess, in a way. In that one, you use the definition of the prefix to get your conversion factor. And then you do it like a unit conversion. Okay, so let's do B and C, and then I guess D, because D is the one that's sort of different from the other ones. Okay, so what we're going to have to use here, there's a kilo, and then I'll start with B. So we're going to have to use, for B, we're going to have to use kilo, and then we're going to have to use milli. Okay, so kilo means times 10 to the third, and milli means times 10 to the minus third. So the first thing we're going to do is go from the prefix of kilo to meters, and we can just do this. I said that's the easy direction. All we're going to do is replace that K for kilo with times 10 to the third, because that's its meaning. So this is equal to 15.5 times 10 to the third meters. And then you're kind of done. I mean, that is the answer. It's just not in nice scientific notation yet, and it's not in standard notation. It's sort of partway in between. So you want to go to one or the other. I guess I'm going to go to scientific notation. So the way I'm going to do that is, in order to have one leading digit on this number on the left, I'm going to move the decimal point over to the left. That's like dividing by 10. So that means I have to multiply the thing on the right by 10 to keep it the same number. And so this is going to be 1.55 times 10 to the fourth. Well, that's, now we have it with no prefix. And so now I'm going to go to the prefix, and I'm going to use the fact that, so we want to have it in millimeters, okay? Well, 1 millimeter, if you use the definition of that milli prefix, is equal to 1 times 10 to the minus third meters. So that's where my conversion factor is going to come from. Okay, so I'm going to start with 1.55 times 10 to the fourth meters. And now I'm going to do this like a unit conversion. I'm trying to cancel the meters, so I'm going to put 1 times 10 to the minus third meters in the denominator. And I'm going to put 1 millimeter in the numerator. And we're left with the units we want, millimeters. Now it's just a matter of doing the exponent rules. So remember, for the exponent rules, if you have some, I'll call it b for base. So if you have a base to the power of m, and you multiply it by that same base to the power of n, the rule is that the answer is that base to the power of m plus n. And for division, if you have b to the m divided by b to the n, that's equal to b to the power of m minus n. So that's what I'm going to do here. My base is 10. And so this is equal to 1.55 times 10 to the power of 4. We're dividing, so this is minus -3. And so you get 1.55 times 10 to the 7th millimeters. Any questions about that? Okay. Let's do, so C is similar, but we're going to microns instead. So we're going to use the fact that micro means times 10 to the minus 6. I guess before I wrote it out. So micro, that's the meaning. So again, we're going to start with 15.5 kilometers. And we want to go to meters is our first step. And it goes exactly the same as it did before. So this comes out to be, 15.5 times 10 to the third meters. And then in scientific notation, that's 1.55 times 10 to the fourth. And now I want to go to what looks like micrometers. You would think micrometers, but people call it microns just to make it confusing. But we're going to think of it as micrometers. So we'll start with 1.55 times 10 to the fourth meters. Before I do this, let me write the equality that we're going to use. So from this definition of microns, we know that 1 micrometer is equal to 1 times 10 to the minus 6 meters. And so now I'll start with 1.55 times 10 to the fourth meters. And I want to cancel the meters, so I have 1 times 10 to the minus 6 meters in the denominator, 1 micron in the numerator. And this is 1.55 times 10 to the power of 4 minus -6, which is 4 plus 6. So this is 1.55 times 10 to the 10th microns. And then with these, I think it's always useful at the end to just ask if your answer makes sense. You know, if something is 1 meter, it doesn't make sense for it to be a tiny fraction of a micron. You know what I mean? So just glance at it and just make sure the numbers are going in the right direction. If in this case, we're going from kilometers, something huge, to microns, which is something tiny. So we expect it to be a big number of microns to fill 15 kilometers. You know, if you've ever run a 15-kilometer race, you'll never think you're going a fraction of a micron. You know, so and we get, just roughly thinking about it, what we expect, a huge number of microns to fill 15 kilometers. You know. Okay, let's do the one that's like a unit conversion now. This was D. So we want to go from 15.5 kilometers to miles. And we're going to use that 1 mile is 1609 meters. So the first step is to go from kilometers to meters, which we've done now twice, and it's exactly the same. So 15.5 kilometers is 1.55 times 10 to the 4th meters. And now it's just a unit conversion. 15.5 times 10 to the 4th meters. We want to cancel the meters, so we're going to put 1609.344 meters with 1 mile in the numerator. Those cancel. And this one, I can't do that in my head, but anyone have a calculator? Can you divide that for me? 15.5 times 10 to the 4th divided by 1609. Oh yeah, I have a phone. I didn't think of that. What is it?
I said it should be 9.63, but I don't know if I did.
Oh, okay. Let's, okay, so we got 15.5 times 10 to the 4th divided by 1609.344. So yeah, oh, I got 96.
Shouldn't you have 1.55 times?
Yes, yes, thank you. I wrote that decimal in the wrong place. 1.55. Okay, so yes, it's 9.63 miles.
But in scientific notation, it would be 10 to the 0.
Yeah, that's right. So remember that anything to the 0 power is 1, so 10 to the 0 is just basically saying that it's, you know, you're multiplying it by 1, yeah. Any other questions on the homework assignment? Yeah.
I have a question about, problem 4. Is there a spelling error, or is it supposed to be negative 9.8 meters per second squared?
Well, yeah, I did mean to put that negative in there, just,
Making sure.
yeah, because we're going to, with the coordinate systems and stuff, we're going to usually we're going to have a negative there. So, and just as a reminder that the negatives just carry through all this stuff, yeah. Any other questions? Yes?
For the one number 8, would it be fine to use 15.5 times 10 to the 3rd? Or it should?
Yes, that would be fine to use just in your final answer, convert it to actual scientific notation.
Okay.
But as an intermediate step, sure, that's fine, yeah. Any other questions? Okay.
One more.
Oh,
Go over the last one.
yeah, the light year one, okay. That is not a great question, I must say. Whoever wrote that question really dropped the ball, I think. I don't know, I think I thought it was gonna be cooler than it ended up being, and then I just didn't change it. Okay, so, the distance light travels in a year is this. Well, that's what a light year is, so you get to see what a light year is. And so you can think of it like this, as a speed. You can think of this as 9.461 times 10 to the 15 meters divided by 1 year. Okay, and now we want to convert that to meters per second. We already have the distance in meters. So to convert it, we just have to change the years to seconds. And so I'm going to do something like this. 1 year is equal to 365 days. I think really you should use 365.25, but this is fine. 1 day is 24 hours. One hour is 3,600 seconds. So that's what I'm going to use. So first I'll use 1 year is equal to 365 days. Then I'll use 1 day is 24 hours. And then 1 hour is 3,600 seconds. If you do the cancellations, you see it does what we want. So we have meters, that's good. We don't have to mess with that. Years, we want to cancel. Days, we want to cancel. Hours, we want to cancel. We're left with seconds. And so our final answer is in meters per second. Yep.
All right, do you have to go through all of those steps if there's year in front?
Oh, I gave it to you. Oh, yeah.
Okay, so you can.
I just didn't read that.
Multiply it, right?
Yes.
Okay.
Okay. Don't do all that. But you could do it that way if I hadn't given you how many seconds there are in a year.
But if it's already in the equation, you can just cross.
Yeah,
cross
let's
it out, right?
let's not do all this. Let me change that. Yes. So instead, just go. We want 1 year is equal to 31,556,926 seconds. The years cancel, and you get the same result a lot faster. And you get something that's about 3.00 times 10 to the 8th meters per second. So the speed that light moves is about, 300 million meters per second. That's fast, yeah. Light moves super fast. That's the take-home message. Okay. Any other questions about this assignment? The fact that people can measure that is pretty amazing. And people measured it very accurately in the 1800s. People are smart. Not all people. Okay, so now we're going to go on to particle kinematics in 1D, which you could think of as really like, in a way, our first real like physics topic. You know, the rest is sort of science related. So particle kinematics. In 1D. And so that's a short little statement, but it has a lot of meaning in it. So let's talk about what these things all mean. So the first question is, what is a particle? And you know, you've heard of particle physics, and that's the study of very tiny subatomic particles. And so you might think a particle is something very small. What I want to point out is that a particle really is not about what the object is. Really, a particle is a mathematical treatment of an object. And so, like for example, if you're doing calculations about the motions of planets, you actually treat the planets as particles, not because planets are really small, you know, compared to everything we're used to dealing with. Planets are ginormous, but just because this mathematical treatment allows you to calculate the things that you want and not worry about stuff that you don't want. So remember, first of all, a particle isn't necessarily a tiny thing. It's just a way that you treat things. But that mathematical treatment is that these objects, so we treat objects as having no length dimensions. So you can think of it as mathematically, we're treating it as being very small. Okay. And so a particle we're treating as being the size of a point. And that point has to be located at the object's center of mass. Okay. So for the first a pretty big chunk of this class, we're just going to be dealing with objects where we can do the calculations by ignoring all their size, okay, and just treating them like points that are moving around. And the location of that point is their center of mass. So like in cases where the object that we're doing calculations about is a person, we're treating, like if a person's just standing there, their center of mass is about, you know, somewhere in here, the top of your stomach, something like that. And as you move around, your center of mass sort of moves around. You know, if both my arms are over here, my center of mass moves over here a little bit. But one thing to remember, I guarantee this is going to come up on at least one quiz. So here's a free quiz point. Particles do have mass. So they don't have size, but they do have mass. Okay, one other thing we're going to see, I'm not going to write this down now, we'll talk about this more later on, but we're going to see that because we treat particles as having no length dimensions, we really can't do any calculations involving changes in orientation. We can't really differentiate in a particle between the top and the bottom or the left and the right. It's all just a single point, okay? So later on, when we want to do calculations involving a body changing, spinning or whatever, rotating, we're going to have to use a different mathematical approach, okay? So the next thing in this statement is kinematics. And kinematics you can think of as describing an object's motion. So it's describing motion without considering the causes of the motion. Okay, so describing motion to us is going to mean talking about the position, velocity, and acceleration. And the causes of motion that we're not going to be dealing with yet are force, mass, energy. There are some other ones, but those are the big ones. So for now, we're just doing the stuff in red. We're ignoring the stuff in the green. Old physicists got to name everything, and I just really would like to state my opposition to their naming on this, because kinematics is just position, velocity, and acceleration. When you add in force, mass, and energy, that's called kinetics. So it's absurd that these two are so similar. There's no reason for that, but we're doing the one with the extra little ma in there now. Okay, kinematics. Later we're going to do kinetics. And then the last thing in this statement is 1D. And I'm going to say for us, just think of 1D motion as motion along a line. In fact, 1D motion, if you're being really technical about it, 1D motion is any motion where at any point the object only has two choices where it can go, either sort of forward or back. So if you imagine a wire with a bead that can slide along it, even if that wire is bent, that bead at any point only has a choice to go this way on the wire or this way on the wire. Are you with me on that? And that's also 1D motion. But we're just going to deal with cases where that 1D is a line. Okay, so a line has that property. If you're confined to a line, you either can go this way along the line or this way along the line. And so the measurable quantities that we'll discuss are position, velocity, acceleration, and how these things vary in time. So time is the last one. Okay. So I'm really just going to go through a list of defining these things. I'm going to start with position, defining what position is. And I'm going to talk about position's relationship with time, and then we'll go into velocity and acceleration. And eventually we'll be able to do some calculations. Let's see, what was I going to say? So I want you to notice that physics is really like you have to kind of force the point to put numbers onto anything, like it's not really inherently mathematical in any way when something moves around, There's no, like if something's moving around, it doesn't have a position, a value that's position at every point. That only comes about from you making certain definitions, okay? So I'm gonna start by saying like, okay, position. So say we're looking at some object and we wanna do some calculations about its motion. The most basic thing we need to do is put a numeric position onto its location at some instant. So how do we do that? So let's say that we're tracking the motion of a train, and I'm using a train for two reasons. One is because I know how to draw it. But then the other reason is the train is on a track. And so a track is very clearly one-dimensional motion. It can either go forward or backwards along the track, I can only draw like old-timey trains, like with a evil villain shoveling coal into it. Okay, so what does it take to put a position on this, to figure out numerically what the position is of this train when it's at this location right here, okay? So first of all, we're going to treat this train as a particle, which means that its location is the location of its center of mass. So let's say that its center of mass is somewhere like here. And by the way, this is the symbol for center of mass. If you ever see this on like crash test dummies, that's what these things are. Though that symbol is telling you the center of mass of each part of the body. And crash test dummies have those all over the different parts of the body so that you can do physics calculations based on what happens in the video. So how do you assign a numeric position to the train's location? Okay, so the train is there whether you're watching, doing physics or not. But how do we put a number on this? Well, it takes two things. So you need to choose two things. The first one is you have to choose a location, and in parentheses, I'm going to say this is like in the real world. That doesn't make too much sense yet, but I'm going to keep saying that, and hopefully I'll be able to clarify why I keep saying that. So it's the location that we're going to call zero position. Okay, so what's the zero position is a reference point. Reference point. And then the other thing we have to choose is a positive direction. I'm going to say positive, And once you choose the positive, the negative is just the opposite of that. So in parentheses, I'm going to say and negative direction. And these are also in the real world. What I mean by in the real world is like, you could imagine, like we won't usually do this, but you could imagine actually painting a dot on the train tracks at the point that you're calling 0. And you could imagine painting an arrow on the train tracks in the direction that you're calling positive, okay? It's an actual existing set of things that you're defining. And so once you do that, let's say that my 0 position is going to be here. So I'll give that this origin symbol. And that's supposed to be a straight line. And I'm going to call positive this way, so negative is the other way. So I guess I'll say this is negative. And now that I've done those two things, in whatever units I'm using, I can just measure out where the train is numerically. So let's say this is 1 meter, 2 meters, 3 meters, 4, 5. Let's say that's exactly 6 meters, okay? So we started at 0. We went 6 meters in the negative direction. So if you go 1 meter in the negative direction, you're at -1, -2, -3, and the location of the train at this instant is -6 meters. Okay, so choosing that 0 position in that positive direction allowed us to measure the position of the train. And I just want to point out, so we're doing this mathematically, but this is exactly what you have to do anytime you're describing where something is. Like if someone asks you, where's my bike? You know, you say like, it's on the far corner of the garage or whatever, you know. The door to the garage is like your reference point, your 0 position, and the far side is getting at a direction that you have to go, you know. So this is to give a direct position. Let me say something about position first before I go on. The units for position are always units of length. So that could be feet or miles or meters or inches. In SI units, that means positions are given in meters. And that's what I gave here. Okay, if you also, besides choosing that 0 position in positive direction, if you also choose a 0 time, you can plot an object's position on a position versus time graph. Okay, so you can think of this 0 time as being when you click on the stopwatch. Uh, so you're sitting here holding a stopwatch, and at 0 time, that's when you press down the start button. And now the time is running after that. Okay. So, for example, let's say at time equals 0, an object's position is negative 22 meters. At time equals 1 second, the object's position is negative 15 meters. At time equals 2 seconds, the object's position is negative 20 meters. And so you could draw this on a position versus time graph. We're always going to have position on the vertical axis and time on the horizontal axis. And I have 0, 1, 2 seconds. And the positions I have are, let's say there's 5, 10, 15, 20. Here's negative 22, negative 20, negative 15. So at time equals 0, I said that the position is negative 22. At time equals 1 second, I said the position was negative 15. At time equals 2 seconds, I said the position is negative 20. And then these would be connected in some way. We don't know what the motion looks like, so I'll just draw straight lines between them. Can anyone think of a reason why we would always put the position on the vertical axis and time on the horizontal axis? I mean, you could just think of it as like sort of an arbitrary rule that we're going to follow, but there really is kind of a mathematical reason. So remember in math, when you first talked about functions, you were introduced to functions as like relationships between variables where at a given, I guess you probably called it the independent variable, at a given value of x or t or whatever, you could never have two different values of the function. Remember that? Well, that's the relationship between these two things. At a given time, a single object can only be in one location, okay? You can't have something at two locations at the same time. And so position is a function of time. And that's why we write this, that's why we draw this graph as if position represented the function and time represented the independent variable, okay? A couple other things about this. So to define position, I had to give a 0 position and a positive direction. Why didn't I have to do that with time? With time, I only had to give a 0 time. I didn't have to, what?
Can't be negative with time.
Yeah, so yeah, time is just always going to move in the positive direction. And like you said, we're never going to think about negative time. So this part of a position versus time graph is never going to exist. If you ever draw a graph and there's stuff over on the left side of the graph, that should trigger like something went wrong on this, okay? Okay, so now I'm going to put this stuff together, and this is a type of problem that I'm going to give you for your homework before the next class. So let's say that there is a straight line between these objects I'm going to draw, and let's say there's a shed over here. And then 15 meters away is a fire hydrant. And then another 10 meters away is a car. So this distance is 15 meters. And this distance is 10 meters. And let's say that we're observing this as physicists, and we see this person walk from the shed to the hydrant in 15 seconds. From the hydrant to the car in 5 seconds. And then from the car back to the hydrant in 10 seconds. Okay? And we want to draw a position versus time graph of this motion. So draw a position versus time graph. And we're going to do this two different ways. So the first way is we're going to choose our position equals 0 to be at the hydrant. The positive direction to the right. And the time equals 0 when we turn on the stopwatch at the start of the motion. The second way we're going to do this is our position equals 0 is going to be at the car. Our positive direction is going to be to the left. And our time equals 0 is going to be 5 seconds before the start of the motion. And so all the stuff that I've drawn up here, this is irrefutable. As people taking measurements, we don't have any control over the distances between things or anything like that. But the stuff in A and B we do control. And we're going to see how those choices affect what this graph looks like. Okay? Okay, so no matter what we call zero position, what we call positive direction, the person starts at the shed. We don't have any control over that. And the person goes to the hydrant, goes to the car, back to the shed, back to the hydrant. We don't have any control over that stuff, okay? So I'm gonna start by just drawing like a kind of a schematic. So I'm gonna take out all the details, and I'm going to, let's see. Here is the shed, here is the hydrant, here's the car, okay? And we have these distances between them. This is 15 meters. This is 10 meters. And now I'm going to draw kind of a little shorthand of what the motion is. So the motion starts over here at the shed, gets to this point in, what did I say, 15 seconds? So to get from the shed to the hydrant, this is 15 seconds. To get from the hydrant to the car is 5 seconds. And then to get back to the hydrant is 10 seconds. Okay, so that's sort of like a simple little schematic that describes all the information that we can't control, okay? And now in red, I'm gonna label the stuff that does depend on our choices, okay? So for part A, what did we choose as our zero position? Hydrant. So I'm gonna call this point here, whenever this person is at this point, they're at zero.
Can you, do that? Oh,
Scroll up.
yeah, perfect. Well, yeah, that's okay.
Okay.
Yeah, we're good.
Okay, so anytime the person is here, they're at zero. What direction is positive? To the right or the left?
Right.
Right. So, okay. This direction is positive and this direction is negative. So this lets us label the positions of these other points. If you start at zero and go 10 meters in the positive direction, what's the position?
10.
Positive 10, exactly. So this is positive 10 meters. And on the other hand, if you start at zero and go 15 meters in the negative direction, where are you? Negative 15. Anyone have any questions about that right now? Are you following the thought process there? And now let's think about the times. At what instant do we turn the stopwatch on?
When you start moving.
At the start of the motion. So I'm going to say my zero time is right here at this instant. Okay, I'll call that 0 seconds. And if the stopwatch starts running right at the start of the motion, what does the stopwatch say 15 seconds later? 15 seconds. Okay. Then if 5 more seconds go by, what does the stopwatch say? Yep. And then if 10 more seconds go by, what does it say? 30. Yep. Okay, so now I'm gonna do this sort of middle step of just writing out this table where I list out the times and the positions along this whole motion. Okay. And what I'm going to do is I'm just going to, oh, you can't see that red very well, can you? That's too bad. Can you tell that these are red?
Yeah.
So what I'm going to do now is I'm going to just start here and I'm going to read off at every one of these points I'm gonna read off the time, and I'm going to drop down and read off the position. Okay? And you might think, you might think this motion always has to start at a position 0, but notice that that's not true. Where we choose the 0 position doesn't have to be where the motion starts. Those are independent things. So like in this case, the motion starts when the person's at negative 15 meters, okay? There will be times when we choose our 0 position at the location where the motion starts, but there's no reason it has to be the case, okay? Okay, so the first point in this motion is at time 0 seconds. If you drop down, what's the position corresponding to that time?
-15.
Yep, negative 15. Negative 15 meters. The next instant that shows up here, what's the time? Yep. And what's the position corresponding to that? 0, yep. Next is this point. What's the time? Yeah, 20 seconds. And what's the corresponding position? Yep, oh, computer crash, pseudo crash. So yeah, positive 10 meters. And now the next point is this 30 seconds. And if you drop down, what's the position at this 30 seconds?
0.
0 again, that's right. So you can't repeat times because time just keeps marching forward, but those positions can be repeated, okay? And now that we have this list, it's just a matter of plotting this stuff out. So we have position on the vertical, time on the horizontal. The times that I have listed here are 0, 15, 20, 30. So I'll make this is my 15 seconds, 20 seconds, and then this is 30 seconds. And then the positions I have are negative 15, zero, and positive 10. And so now I'll just plot these out. I guess I'll do it in green so you can see it a little better. So at 0 time, the position is negative 15 meters. At 15 seconds, the position is 0. At 20 seconds, the position is 10 meters. I'm going to move this 20, get it out of the way. And then at 30 seconds, the position is 0. And if you connected these, if it was realistic, these would be curved. But we don't know what the curves look like, so I'm just going to draw it like this. Straight lines between these. Any questions about that? So with that choice of 0 position, positive direction, and 0 time, this is what the graph looks like. Now for part D, we're going to make those different choices and the graph will look a little different. There'll be some things that look the same and some things that look different, okay? So for part B, I'm going to start out with the same stuff we knew before. And I'm gonna erase all the red stuff because remember all the stuff I put in red, I said, depended on our choices. So this motion is still exactly the same, so that's all still stuff that is the same. And so now for part B, what did I say we chose as our 0 position? Car. So over here, I'm gonna call this position 0. And what did we choose as our positive direction? To the left or right? Left. So positive is to the left. That means negative is to the right. And based on this now, we can label these other positions. If you start at 0 and go 10 meters in the positive direction from 0, what's the position here? Positive 10. And now if you start at 10 and go 15 meters more in the positive direction, what's the position here? 25, perfect. Okay, and then, so that's all the positions, and now we have to think about the times. So this time I said we click on the stopwatch 5 seconds before the motion starts, okay? So in other words, what does the stopwatch say when motion starts? If you click it on 5 seconds before, you're just waiting for motion to start. 1, 2, 3, 4, and the motion starts on 5, right? So the stopwatch says 5 seconds when the motion starts here. 15 seconds after that, what would it say? 20 seconds. 5 seconds after that, 25. And 10 seconds after that, 35. And so now we can do the same thing we did with the table. And we're just going to go to every known point along this motion. So at that first point in the motion, the time is 5 seconds. What's the position? 25 meters, yep. At the second point along the motion, the time is 20 seconds. What's the position? Positive 10 meters, yep. Next, we're at 25 seconds. And what's the position? 0 meters. And then finally, we're at 35 seconds. And what's the position? Positive 10, perfect. And now it's just a matter of plotting that out. I'm gonna do that over here so that I can bring the other one over and we can look at them. So position is on the vertical axis, time is on the horizontal. The times we have are 5 seconds, 20 seconds, 25 seconds, 35 seconds. Wait, 5, 20, I made this one too far away. 25, 35. And then the positions are 0, 10, and 25 meters. And now we can plot these. So at 5 seconds, we're at position 25. At 20 seconds, we're at position 10. At 25 seconds, we're at position 0. And then at 35, we're at position 10. Let me bring down the one from part A so we can compare these. So notice there's nothing like universal about that position versus time graph or any of the positions or anything like that. The position totally depends on our choices. And these are choices we have to make before we can do the problem. But there are some sort of universal things that are similar. Like you can tell that those shapes are the same, right? So what did our choices do to change these two graphs? Well, changing our 0 position has the effect of shifting the graph up or down, okay? Changing our positive direction had the effect of flipping the graph upside down. And changing our time equals 0 had the effect of shifting the graph left or right, okay? But if you forget about the flipping and the shifting this way, you can tell that those shapes sort of get at something that's consistent between these two motions, you know? Okay, anybody have any questions about that example? Yeah.
Yeah, so I guess when I pick direction left or right, I think negative left, off or right.
Yeah, right. You're used to thinking about that like on number lines and on coordinate systems and stuff. So physics is confusing because in math, you don't ever have to go back and forth between the real world and math world. Everything's in math world, you know? In physics, you do have to go back and forth between those two. So there's a real world where we're saying, like for part B, we're saying positive points towards the apple tree or whatever, you know? And we're not used to that. In math, you're not used to that. In the world where your graphs live and stuff like that, positive always goes to the right and positive always goes up. But so in your mind, you have to sort of try to make the distinction between, am I drawing a sketch of the actual orchard with a cat sitting there and whatever? That's the real world. Or am I doing a graph that lives in math world, you know? And the rules are different in those two worlds, you know? And it's just hard for everyone to get used to. But I think you will get used to it without much trouble. It just takes a little time, you know? Any other questions right now? Okay, well, let's stop there and I'll give you 1 or 2 problems like this to do. And then I think on Monday, we'll be able to start doing actual calculations, hopefully, by the end of the class. Okay.